Would you agree that when you hold a spring downward, it pushes back up? There are two opposing forces here, the push of your hand downward and the push of the spring upward. When the forces are equal, the net result is zero change in motion. And because there is no relative motion, you've got static equilibrium. At the level of the very small, guess what the table's made of? Tiny, tiny atoms, which in many ways behave like powerful, tiny springs. A book at rest on a table pushes downward due to gravity. Meanwhile, there's an equal push upward by the zillions of atoms within the table. When the forces are equal, there's no change in motion. Again, you've got static equilibrium. The book pushes downward because of gravity, right? We call this the book's weight. Meanwhile, the surface of the table pushes upward because of the electrical force exerted by the squashed atoms. It works against gravity, and we call it a support force, which physics teachers call a normal force, because it's at right angles to the supporting surface. Stand on a scale, and your weight pushes the scale downward. This is a gravitational force. The floor beneath pushes back upward, which is the support force. And in between you and the floor, the scale is getting scrunched. The more you weigh, the more the scale gets scrunched. This impacts its internal springs and other mechanisms, which are calibrated to provide a readout of the degree to which it is getting scrunched. And as you stand there, notice that you're holding still, which means no acceleration, which means no net force. What if you had each foot on a different scale? Would there still be no net force? What would these scales read? What if you stood on two scales set on top of each other? Would these scales show the same reading? Think about that. Good energy.